We're with Power Systems. We're a systems integrator. Mainly work on kind of tailored automated manufacturing solutions. Everything from like a micro level all the way up to large scale equipment. So think medical devices, aerospace, all the way up through nuclear handling. We've got a couple of issues that we want to present, kind of how we attack them. So I've got Ryan and Danny are here with me. There's some from our engineering department, obviously an engineering fellow and one of our senior software engineers. That's what we said. You know, what grade was that taken in? Now, so these guys are going to really focus on the content, kind of the problems, and how we attack them a little bit. I'll let them introduce themselves when we get to their briefs, and I'll hand it off to them. I'm going to give you kind of a quick introduction to PAR, give you a little bit of context of why we're looking at these things. And then, like we talked about, Ryan's going to talk about an automated process that we can put into play to look at the different, how do we automate a line. And then Danny's going to talk about some of our technology, our visioning and AI technology and how we apply that. And then if anybody has interest, we have some specific examples. So thank you all for being here. We'll jump into this. So PAR Systems, we're an advanced manufacturing company. We've been around for about 60 years. We actually we got our start in Minnesota, and that's where we reside today. Let's see here. We're about 500 people strong in a large technical community. We have 4 critical areas that we focus on. Our automated assembly is mainly like medical devices. You can think of kind of batch processing and then doing a full linear integration of medical devices. Advanced manufacturing is kind of where we all sit and kind of focus. That's looking more at the kind of the aerospace industry, the defense industry type areas, and how we modernize that production. And then the nuclear it's called nuclear handling. So basically automation inside nuclear facilities, handling some of the critical infrastructure and critical things in there. And then we've got a group that's called Schuette, and they actually produce parts for the marine environment, but it's largely for the Navy. Big picture there. So we work in very highly regulated industries: nuclear, FAA, aerospace, medical kind of industries. Some of our capabilities outside of just producing things, we also have labs, our robotics labs, our vision lab. We do some experiments and work with some of our customers in the labs. We have a friction stir welding lab, which is staying very busy these days. And we're a center of excellence for several proof of concepts and process development with different customers. We have on-site training both in our facility and at the customer's facilities. We do maintenance training, and then the biggest thing that we're probably most proud of is our field service and support. So once we deliver a system, we have a 24/7 hotline. You can call us to get support. We've got field service teams all over the world, take care of the parts and pieces. As we talked about, I think most applicable to probably this group is our what we call auto assembly. It's actually line integration, and what this system does is basically brings together several different areas of automation to assemble a medical device and package it. So you're taking from bin parts all the way up to a packaged item. And then we talked about the advanced manufacturing area. So like I said, this is kind of where our briefs are going to be at today, is we're looking at how we did things in kind of the aerospace industry, and where we think automation is going, and how you can apply some I would say some discipline into how you automate your systems. All right, so with that, I'll hand it over to Ryan and let him introduce himself. And again, thank you all for being here.
All right, I'm Ryan Schuette. I'm with Power Systems. I've been with the company about 16 years. I'm an engineering fellow, and today I'll be walking through our work that we did. Automated installation of fasteners and aircraft assemblies. Specifically where traditional automation wasn't feasible. This is a case study in how we approach solving difficult automation challenges. It also highlights how tight collaboration between us and the end user results in smoother program execution. Military aircraft designs push automation to its limits. Their designs do not put manufacturability as a priority. Tight access among other tangential processes make automating traditional fastening techniques not feasible. This project, through collaboration effort between Lockheed and Power, tackled those challenges head on. We began by breaking down all the tasks, identifying risks, and running POC studies, very targeted POC studies for all of these tasks. Due to factors like limited space and the number of different processes needed to be automated, drove us to develop modular single function end effectors, interchangeable end effectors that could share workspace and common platform. This is a flowchart we developed with the help of Lockheed, and this helped us evaluate the feasibility of automating these processes. This is a flowchart we would revisit regularly with Lockheed. But this is a tool we would develop for any program level process automation. Again, it's just something we could come back to and reevaluate as we look at all these tasks and processes and make sure that the program was still heading in a direction that made sense. With help from Lockheed, we categorized all the tasks once we identified them all as Tier 1 and Tier 2. Tier 1 were tasks that needed to be automated in order for an automated work cell to make sense. Tier 2 tasks were more optional, but a certain number of those still needed to be automated in order for a work cell to make sense. So again, when we're looking at automating processes or an entire work line or a system, this is another technique we would use. We'd categorize things as Tier 1, Tier 2, or maybe 2 or 3, and it would help us guide the program and where our POCs needed to start, which ones we needed to tackle first, which ones were important for us to get really well defined before we moved on to Tier 1. If we couldn't do a Tier 1 task, the program was just dead. There's no point in automating. From the start, this was a partnership with Lockheed. Lockheed helped us understand the specific task requirements. They also helped us develop technical concepts, and we reviewed them regularly with Lockheed to make sure that what we were doing still made sense. Iterative prototyping, validating each step inside of our labs at Power Systems. Helped us develop reliable designs, robust designs, and designs that were ready for, were industrially hardened before we ever integrated them into a full work cell. Due to extreme space constraints in this particular case, large multifunction end effectors that would be more traditionally used were not feasible. Again, that's why we elected to go with single-purpose modular end effectors, each with a single process tied to it. This also made the work cell flexible and scalable. If you wanted to add a process, all you had to do was incorporate a new end effector that mounted to the common motion platform. If you wanted to eliminate a process because it was no longer making sense, you could also just pull that end effector out. So in this particular case, one of our biggest constraints was physical access. We had multiple tools to fit into tight, irregular spaces, but we still needed to keep cycle time in mind. This is where our modular end effector philosophy really paid off. The other thing is, again, if you wanted to add processes or you wanted to modify how that process worked, you didn't have to modify a large, complex, multifunction end effector. You could just redesign a much smaller, cheaper end effector, or you could just eliminate it and redesign it completely. So one of the important tools here is simulation. Senate, one of our suppliers, they make CAM software and simulation software. We worked with them to develop a new piece of analysis software that was called Pathfinder. This helped us identify accessibility of our end effectors. Again, tight access was one of the big challenges. So very early in the process, we could put our geometry of our end effector into this Pathfinder software. It would drive to all the points of interest in the assembly. and then it would tell us if it would be able to access those points without interference. Again, doing this early in the design cycle in virtual space really helped modify our geometry of our end effectors and be able to tweak them very quickly with very little cost. Another reason for the accessibility studies, they also supported Lockheed's ROI and justification. We could show them with very detailed reports exactly where we could reach in the assemblies, where we couldn't, the percentage of these fasteners that we could automate the installation of. Again, that helped Lockheed continue to justify the program with an ROI calculation. This kind of information early and often developed helped keep Lockheed informed, and it was a solid metric for them to evaluate the performance of the program and the automation effort. Don't need to spend a lot of time on these. This is just the overall work cell concept that was developed. Again, we have common motion platforms that could pick up a whole array of different end effectors for different processes. This particular assembly required 2 robots working in concert on either side of the assembly because you have two-sided fastening, you have a nut and a bolt. So the robots that work in concert. There's also 2 more robots that would do all the handling and fastener prep steps. Like I said, there's a lot of ancillary processes, so all the fasteners before they're installed had to have preparatory steps done to them. So that's why we had a handling robot. Here's a video of the whole process. Yeah. So again, a lot of different processes. This is a mock work cell that we set up in our lab in Minnesota. The first step is locating the assembly, so we have some vision systems that would go and locate the assemblies. And then the next video clip will show the interchangeable tools being automatically dropped off and picked up by the motion platform. One of the first steps that you'll see is the holes would get fouled with a sealant when they made the skin to the structure. That sealant had to be cleared from the holes before the fasteners could be installed. So we had to develop actually 3 different techniques to clear the sealant. The first one was something called NPSR, negative pressure sealant removal. This would feed a tube of disposable polyurethane tubing into the hole while drawing vacuum, and that would remove the sealant from the hole and be a nice clean hole. The next process you'll see, this only works if the sealant is early in the cure cycle. Later in the cure cycle, the sealant would have to be removed more mechanically. That's the next clip you'll see. Yeah, so this is the auger tool. This tool would pick up a plastic auger tool that would actually ream out the sealant from the holes. Everything that touched sealant was going to be disposable because sealant is not easy to clean off of things. So the machine could automatically install and remove its own disposable tooling. And in this case, it will take that tool and literally drill out the hole with a plastic disposable drill bit while collecting the sealant to eliminate fog. The sealant would also follow the countersink regions, so we came up with a countersink cleaning tool, and this would use a fiber rope that we push into the sealant, into the countersinks, do a spin to wipe the countersinks clean, and then it would advance the rope being the disposable, and to use a clean piece of rope for each one. This is a temporary fastener removal. There's temporary fasteners called clecos, and those get removed automatically with this end effector. It's almost. So this is our fastener handling end effector, and this just picks up a fastener out of a tray and adds a bead of sealant. That's the preparatory step I was referring to earlier. After this step, it just gets handed off into the installation robot and installed into the assembly.
So hey, thanks, Ryan. That's good stuff. So the big takeaway there is not necessarily what the system is doing, but from PAR, the takeaway is that there's a process that you can apply to any line, any type of manufacturing, process that will allow you to determine how you can go about automation. I think traditionally, a lot of times we've just put a robot or some type of automated equipment into a line, and then we say, okay, now we're automated, and that's led to a lot of different problems. So what we like to do is more of a systems engineering approach to look at the entire process, kind of end to end, and say, where can we automate? Where is there, what lends itself to automation? Even looking at how is the part itself designed? Is it designed for automation kind of thing? So takeaway from Ryan's brief is just, the more work you do on kind of the front end to determine where the automation applies, and then also using simulations allows you to really learn a whole lot about it, but also allows you to justify investment kind of up the chain. So next we'll look at, Danny's going to talk a little bit about some kind of a technology advancement that will allow us to do some additional things. And so with that, I'll turn it over to Danny and let him introduce himself.
Hey, good morning, everyone. My name is Danny Langan. I am a software engineer at PAR Systems. What I really like about what Ryan just showed is all the processes and complexity that you see that go into creating an automation cell for one part or a part within several variations. So with that kind of part where a single assembly has thousands and thousands of holes, it's very critical to get it right, but also one of the benefits there is that we have the CAD model and we have the part program that we know where that part is, how we go up to it, so we can get in the right area whenever we're doing a process. So I spent the first several years of my career working on developing all those little processes, getting it working right, and working with Ryan and the rest of the team to come up with this clean build. But after that, one of our chief engineers, really likes to give me a hard time, make some trouble for me. He says, okay, but what if there are hundreds of different variations of parts that we need to be able to process? And also, what if we don't know what it looks like, what the part program is, what kind of features are where? How do we approach the problem so that we can give the robotic system intelligence so that it's able to come up to a cell either automatically or an operator driving it up to the cell, and it can just figure out what it needs to do from there. So that brought us to our vision mapping and planning system, also known as VMAP. It's an adaptive system that is using machine learning, and it's particularly targeted towards manufacturing spaces where there's a very high mix of parts, variations of parts, where there are different shapes, different sizes, different features and processes that have to be done on them, and there's also a low volume of each of those individual parts. So what that means from an ROI perspective is the part programming every one of those individual parts is time-consuming, expensive. As soon as I have one variation or a change, every single thing needs to be redone, and that's very costly from a human labor perspective and from a schedule perspective. So by using VMAP, we're able to instill the desired task and the learning for the individual parts into a machine learning model so that it's able to approach the cell, take pictures. So this is an example of the VMAP system in our lab at PAR. It's a simple robot. It's got a sensor on there with a camera, and a sealant end effector to do the process. We're using a 2D, 3D camera, a tool changer, so we're able to actively adjust the process for whatever needs are seen by the robot. And then for inspection processes, we have a 3D light structured camera, so it's able to take very high resolution detailed scans of the part before and after a process for inspection. So some of the targets we've used so far in our initial testing are different, various types of fasteners that are used for aircraft manufacturing. That includes rivets, line bolts, and different kinds of threaded fasteners. So lots of different things that are used to assemble the wings, the fuselage, attaching stringers to the skin of the body, as well as they have to be highly, a high performance seal for fuel sealing. So walking through the VMAP process flow, in a situation where the part is positioned in the robot cell, operator puts down the part on a table, or the robot cart is wheeled right up to the part. It could be a giant part, and it could just be our small robot on the cart that is then brought to the part, so we don't have to do a traditional manufacturing process where it's a monument system that the part has to be brought into the cell. We're able to bypass that, leave it as a more open floor concept that is more flexible and can vary from week to week or from year to year depending on the needs of the manufacturing space. The operator is able to just initiate the process, or it can be automatically initiated if that is pre-programmed. The robot is able to move through different positions. It takes 2D images from multiple positions, and from that it's able to detect the fasteners, figure out what type of fasteners they are using the machine learning model, and then it's able to estimate the position of each one of those targets, and then automatically build the sequence and generate the optimal paths for that process. So you can see in this situation where we're putting the parts in the cell, they don't have to be in any particular orientation or space, they just have to be somewhere within the view of the robot and somewhere where the robot can then reach them for the process to do after that. We do the image capture process where it's just inspecting the cell, taking from multiple angles to increase the accuracy of the estimation, as well as if there's obstacles in the way of the targets, it's able to reach around and see that just in case it might miss it in one of the images. So we have some redundancy there to improve the accuracy and the quality of the estimation. So this is an optional step where if we are going to be doing some pre and post inspection, we can move up to the part with our high resolution scanner, take images before the scan, and then later on I'll show you what it can do with those images afterwards. So this is the what an operator would be seeing from the automatic view, from the HMI on a system like this. So each one of these fasteners, they might look very similar to each other, but they are actually different sizes. And the machine learning algorithm in this case is able to identify them and come up with what they are, and based off of what it sees, it can decide what processes need to be done to that particular fastener. So once we have all the fasteners that we've identified and they're separated in their different classes, we can automatically generate those paths, and it's going to prioritize one, minimizing tool changes so that it can do all the processes with the tool that it has on there and eliminate cycle time there. It's going to find the quickest way it can move from fastener to fastener to just make that process as efficient as possible. So with the same system, you can then do a process like sealant application. In this case, we weren't actually applying sealant, but it's a mock cap seal, as in a situation where you have a fastener in a fuel cell or a fuel seal area within a commercial aircraft, where every one of those gaps is an area where fuel can escape and potentially leak from the plane if it's not done properly. So it's very important. And in that same, with that exact same process, with the same end effector, we can do something like fastening, where in this case we are able to identify the fastener. We're taking it out because in this case we wanted to clear the panel, but from the individual images, we can find those tiny fasteners and figure out the position and orientation where we need to go to do that process. So that brings us to the other optional step, which is the post-inspection of that VMAP process. In this case, we previously did the scan of the part of what it looks like beneath the fastener, and then also take a scan of what it looks like after the sealant has been added to the part. So from that we can measure, okay, how thick is the sealant on every part of that fastener, and from there we can put rules on what we see from the inspection. Is it thick enough? Is it thin enough? Make sure it's within tolerance, and then provide all of those results back to the quality team that needs to have that information and make sure the part meets the standards of the aircraft. So far with VMAP, we've had a lot of success. We can use the exact same machine learning algorithm to teach what the fasteners look like, or what the targets look like. So using the same algorithm, we can have different types of fasteners that are identified without having to retrain it. And that means you could have multiple different targets within the same work cell. It doesn't matter where they are, what shape the overall assembly is. You can go up, you can see it with the robot. The robot will then automatically decide what to do and then execute the process. The accuracy of the machine learning based pose estimation, there's a couple factors involved: how small the target is, how far away you are from it when you're actually taking pictures. But typically we can get an estimation accuracy of plus or minus 1 millimeter to 4 millimeters, depending on the type. For the purposes of these processes, that is more than good enough. And when it's needed, you can augment the process with even more advanced methods. That just, it's all a game of how much speed tolerates that changes the cycle time and the changes the cost of equipment in the process itself. So really, the biggest lesson learned and the biggest achievement of this system is we can automatically find the parts, we can automatically generate part programs without knowing anything about the part beforehand, and that enables a lot more flexibility in the manufacturing environment that we're able to provide to our customers. So we're currently looking for more partners to use this process with. So training different targets, implementing this system in more manufacturing environments, and just continuing to reach out and improve the process as we go. There are several configurations that you can use with the VMAP process. You can, like I was saying, the more cost-effective method, the more value-based method is put a robot on a cart. That's all you need. It's got a computer. It's got everything on board to do your process. Or you can go the next level of putting a robot on top of an AMR or an AGV, and that allows you to automatically deploy it without having to have an operator present at all. So, big lesson here is we're training the task without knowing the part. We're able to train the task to be able to execute without having prior knowledge, and it doesn't matter how many variations of parts, how many different parts you have. We're able to make it work for all those different scenarios, and that provides a lot more value to the customer. I'll hand it over to Jeremy.
All right, so with that, any questions for Danny or Ryan? So I'll give you the summary of the VMAP part. I think Danny hit it at the end, is basically using vision to enhance operations but eliminate the pre-programmed paths. And so you don't rely on a CAD model, you don't have to stop programming every time a new drawing comes out, or excuse me, you don't have to stop production and do reprogramming every time a new drawing comes out or a new rev. You're able to just keep going because the robot is performing, we're training it, I don't want to say like a human, but we're going to train it to perform a task independent of what that part is. So if it sees that fastener, it's going to do the task that it's trained to do on that specific target. So a very powerful tool that we're applying across several aerospace operations, but you can extrapolate that out to possibly drilling, fastening. Sealant is the one that we're looking at now, but I think there's other applications as well. And I think that's really the end of our presentation. So just come see us at our booth if you want to talk more, and or let us know if you have any questions as we're here. Again, we appreciate the time. Thank y'all.